Hello, calculus students. Here we are with hyperbolas and implicit differentiation. Hyperbolas are a little trickier because they have the asymptotes as part of the graph. And again, we're going to use calculus to find the slope of the tangent line. Here's the definition of the hyperbola, the set of points where the difference of the focal radii is constant. And let's check this out on GeoGebra. If we go ahead and have it set up a ellipse, a hyperbola, and you can get this under the ellipse column. There's your hyperbola. And we can put down two foci and then a point on the hyperbola. Look at this. Wow, all over the place. So now we can adjust the direction of the hyperbola. Notice we line up the foci vertically. We get a vertical hyperbola. If we line them up horizontally, we get a horizontal hyperbola. And let's look at this other idea then about what is going on with the hyperbola. What is this set of points? Let's take a typical point on the hyperbola then. There, call that D. Point on the thing. D. There you go. And let's look at the distances to the foci. So from D to A and from D to B. There's your two numbers there. Now, it turns out it's not the sum that stays constant, but this difference. So let's take a look at this now by looking at D. Let's see, B minus A. B minus A. We get 0.99. And sure enough, as I move D along, even though A and B are changing, their difference is staying constant. Even if we come to the other side here, well, to do the distance, you have to do the absolute value. There you go. The difference stays constant. And now again, we can research where is this, where are the vertices? The vertices are going to be in line with the foci, and where that line through the foci crosses the hyperbola. So let's intersect that line with the hyperbola, and then we get those are your vertices at F and E. And if we look at the distance between F and E, and look at this segment, FE, notice how it's matching that 0.99 from before. Even if we start making the hyperbola different by changing these foci, see how the difference in the focal radii is matching the distance between the vertices, and that's 2a. Okay, back to our notes then. Here's the definition of the hyperbola that we just talked about. Here's the standard forms. Notice the only difference between this and the ellipses is the subtraction. And also, you've got a slight difference here in your a squared b squared formula too. And let's look at that. It is, oopsie, it should be in here somewhere. Well, we'll have to add it. It's on my formula sheet that I gave you in the other one. And there's the asymptotes and so forth. Let's just back up here to a squared plus b squared equals c squared. In this case, c squared equals a squared. There it is. C squared equals a squared plus b squared. Because now c is going to be further from the center than the vertices. Now, I'm going to show you an easy way to come up with the asymptotes where you don't have to do so much equation memorizing. It's just basically the diagonals of the box of extent. Okay? And let me show you in this first example. Okay, in this example, they show how you can go from given information like the foci are -1, 2, and 5, 2, and the vertices are 0, 2, and 4, 2. And from this information, you can figure out that C equals 3. And from this information, you get that A equals 2A equals 4, so A equals 2. And they use that then in coming up with B, the square root of 5, and then that's how you get the standard form. Also, either one of these, the foci, the vertices, in between, halfway in between these two must be the center. The center, then, is halfway between -1 and 5, and halfway between 2 and 2. Well, that's 2. But -1 and 5 is 2, so we end up with 2, 2 for the coordinates of our center. Now, what I like to draw to come up with the asymptotes of hyperbola is the box of extent, the same one we used on the ellipse. That is, from the center, I'm going to go 2 each way with the A, or in this direction, and in the y direction, I'm going to go the square root of 5, which is about 2.5 or 2.2. So I'm going to go that far in this direction too, and I create what I call the box of extent. This would be the box of extent if it was an ellipse, and the ellipse would stay inside this box. but it's hyperbola, so it stays outside that box. And so it's easy to see that we went over 2 and up square root of 5, so that the slope of this asymptote is the square root of 5 over 2, just as this slope will be negative square root of 5 over 2. And so an easy way to come up with the equation of the asymptotes is just using point slope. They both have to go through the center, so you get y minus 2 equals plus or minus square root of 5 over 2 times x minus 2. Point slope comes in very handy because both asymptotes go through the center. Let me show you this on the next example. Now they give you this formula, which is again based on point slope, right? Y minus k equals plus or minus b over a times x minus h. There's your hk is the center. And notice it's plus or minus b over a or plus or minus a or b depending on what type of hyperbola you have, horizontal or vertical. That's hard for me to remember. I mean, you can get it off your formula sheet and so forth. But I'll show you can come up with the hyperbola and the asymptotes for this one. You've got 4x squared minus y squared equals 16. Well, first for standard form, we have to get a 1 on the right here. So we divide both sides by 16. So you get x squared over 4 minus y squared over 16 equals 1. So that's x squared over 2 squared minus y squared over 4 squared equals 1. Now there's a lot you can do right now in terms of this box of extent. See this box right here? The center here is at 0, 0. Center is at 0, 0. Because we're not subtracting anything from the x or the y. And now we're going to go 2 each way in the x and 4 each way in the y. See the 2 each way in the x, 4 each way in the y? Now, one of these is the vertices and one isn't. These are actually the vertices. I'm going to make these open circles here because these points actually don't exist on the hyperbola. They do on the ellipse. And if it was an ellipse, we just kind of sketch in our curvy ellipse inside here. But it's hyperbola, so the diagonals of the box of extent are your asymptotes. So let's draw those in. There's a diagonal. Make another diagonal over here. There's a diagonal. The diagonal of the box of extent are the asymptotes. And let's come up with an equation for these. For both of them, you can see you're going over 2 and up 4. So the slope is 4 over 2 or 2. See, I didn't use a memorized formula. I just look at this, the rise over the run of the diagram. And this is a slope of negative 2. So the asymptotes are going to have equations y minus 0 equals plus or minus 2 times x minus 0, or y equals plus or minus 2x in this case. Now sketching the rest of the hyperbola, we can just go like this. From the vertices, get closer and closer to those asymptotes. Don't cross them though. Keep getting closer and closer. And this is what we call a horizontal hyperbola, because the x squared comes first in the subtraction, and the axis of symmetry is horizontal. And the book agrees. Now here's just a convenient way to do the asymptotes. We talked about that, the whole idea of point slope form using hk in each case. And that's again what I'm saying, use just vertical change or horizontal change. Now, finding the asymptotes of hyperbola. Sketch the hyperbola given this equation. Find the equations of its asymptotes. Oh my gosh. Well, here's again this idea of completing the square. So we've got separating the variables, 4x squared plus 8x plus blank minus 3y squared equals, I'm going to put the negative 16 over here. Now what I'm going to do is I'm going to factor the 4 out of these two, leaving behind x squared plus 2x plus blank minus 3 times y squared equals negative 16 plus blank. Yeah. Now what completes the square here? Well, if we add a 1 here, we're actually adding a 4 to this side, so we're going to have 4 to this side. So we get 4 times x plus 1 squared minus 3 times y squared equals negative 12. Divide both sides by negative 12. 3y squared over negative 12 equals 1. And now we can start talking about what this looks like. Let me put another page of crunching down in between here. That is, it's x plus 1 squared over negative 3 plus y squared over 4 equals 1. I'm going to write it in the subtraction order this way. Y squared over 4 minus x plus 1 squared over 3 equals 1. So therefore our a is first in the order. A equals 2 and b equals the square root of 3. And that's that form they're emphasizing here. We get our center from these ideas, negative 1 comma 0. And we go 2 each way in the y and square root of 3 each way in the x. So that your asymptotes then have a slope of rise over run. So we're running over 2. Actually, we're running over the square root of 3, and we're rising to it. You can see it right from here. Here's your change in y right there. There's your change in x. 2 over the square root of 3. So the asymptotes will be y minus 0 equals plus or minus 2 over the square root of 3 times x plus 1. X minus 1. Now, using asymptotes to find the standard equation gets a little tricky. Find the standard form of the equation of the hyperbola having vertices 3, negative 5, and 3, 1, and having these asymptotes. Well, from 3, negative 5, and 3, negative 1, we can tell that the center is at the midpoint. Midpoint of the vertices. So that's 3 plus 3 over 2, comma, 1 plus negative 5 over 2. So you get 3, comma, negative 2. That's your center. And now you can see that a equals 3 because both these vertices are 3 away from 3, negative 2. But we don't have b, but we do have these asymptotes at 2x minus 8 and negative 2x plus 4. And notice again, you see them crossing at the center at 3, negative 2. And again, there's your 3 for the vertices. How do you come up with b then? Well, we can look at this as the slopes of the asymptotes are plus or minus 2. And it's definitely going to be, the slope formula in this case is, since it's rise over run, we're going to go over the x ones and up. This is going to be a vertical form hyperbola. I'm going to have to pause here to set up my next class. Okay, here we are trying to figure out how to use the asymptotes to get back to the original equation. And we already determined that the slope was plus or minus 2. And if we think of the box of extent in here, what we're missing is the b. We know that this a equals 3, and so we just don't know how far over to go, and that's b. But I think you can see that the rise over the run is going to be a over b in this case. So a over b equals 2, and we know what a is, that's 3, so 3 over b equals 2, so 3 equals 2b, so b equals 3 halves. And that looks about right. You're going over 1 1/2 on the box of extent there. So now you're ready to write the whole equation. And since this is vertical, the y minus k squared is going to come first over a squared minus x minus h squared over b squared equals 1. And sure enough, that's how it's substituted here, with the vertex being at 3, negative 2, a equals 3, and b equals 3 halves. Now, I've seen at least one example from somebody working on WebAssign that gets a little picky on this. Don't put this as a decimal, change it into the fraction y plus 2 squared over 9 minus 4 times x minus 3 squared over 9 equals 1. Just so you don't have any fractions within fractions. Okay? Now, here's where the advantage of calculus comes in. Finding the slope of a graph implicitly. Find the slopes of the tangent line of this graph at the point 5, 2. And let's look at that figure. And sure enough, now you might think, where do these come from? Well, that's because they got into standard form. If you divide through by 64, you're going to get x squared over 16 minus 9y squared over 16 equals 1. Over 64, that is. And so it's x squared over 4 squared, so that's where we go 4 each way in the x. And it's y squared over 64 ninths, which would be 8/3 squared. So we're going to go about 2 2/3. So that's why they went that far in that direction. But let's see what we come up with a slope of 5, 2. It looks like something positive. So we take the derivative with respect to x of both sides equals the derivative with respect to x of 64. So you get 8x minus 18y dy dx equals 0. So 8x equals 18y dy dx, or dy dx equals 8x over 18y, which simplifies down to 4x over 9y. So at the point 5, 2, our slope should be 4 times x, which is 5, over 9 times y, which is 2, and we get 10/9, or a slope of about 1 1/9. And that seems to make sense with the picture. Now I want to do one more from here, and it's the type of question where you're supposed to find out the horizontal and vertical tangent lines. Because this is typical of what I'll expect you to do in the test. Right here. Determine the points at which dy dx is 0 or does not exist as an aid in locating the vertices of the hyperbola. So let's try that on 65 here. We go ahead and start taking the derivative, and it's 8y dy dx minus 2x plus 6 plus 40 dy dx plus 0 equals 0. And it's actually a much easier equation because we get basically 8y plus 40 times dy dx. And let's put this stuff on the other side, 2x minus 6. So we get dy dx equals twice x minus 3 over 8 times y plus 5, or x minus 3 over 4 times y plus 5. Now, how can this help us figure out where we've got horizontal and vertical tangent lines? Well, we know it's going to be a horizontal or vertical hyperbola because of the difference in the squarings. And dy dx equals 0 when x minus 3 equals 0, when x equals 3. So you could put 3 back to the equation and solve for y, and that's where you actually get your vertices then. So let's try that. 4y squared minus 3 squared plus 6 times 3 plus 40 times y plus 75 equals 0. So 4y squared minus 9 plus 18 plus 40y plus 75 equals 0. Let's just keep the y terms. 4y squared plus 40y. So this is 9 and 75 makes, I believe, 84. Divide through by 4, y squared plus 10y plus 21. And I believe that's 7 and 3. So y equals negative 7 and y equals negative 3. And so you get a horizontal tangent line at, 3, negative 7, and 3, negative 3. Now in this case we're not going to get vertical tangent lines because it's hyperbola. You would in an ellipse. You could find the other endpoints in the minor axis with the vertical tangent lines, or vice versa, depending if it's horizontal or vertical ellipse. But let's check this on GeoGebra. Also, it's hard to graph this one in the calculator, but GeoGebra does a pretty good job with this type of expression. And sure enough, GeoGebra confirms that we have our vertices here at 3, negative 3, and 3, negative 7. Notice in a hyperbola, in this case, we won't have any undefined tangent lines. If it was an ellipse instead, then we would expect some undefined, some vertical tangent lines over here and here. Okay, so keep that in mind. You can use calculus to find the vertices of ellipses and hyperbolas, and also endpoints of the minor axes in the ellipse. Flange out.